Good. Thank you for the invitation and the introduction. It's my great pleasure to be here sharing our work. And today I will discuss the urban computing, building intelligent cities with big data and AI. Okay. So traditionally, we have factors of production, including land, labor, capital, and technology. They all have led the previous development of our human history and formed our current society. The data has become a new factor of production, not only in China, but also in the whole world. And it can be anticipated that the data will have a great impacts on humans' current and future development. And its contribution may be so large that exceeds all other four factors combined. And this argument is based on the following observations. First, that the data generation has no limits. Now, tens of billions of sensors are generating data 24 hours a day. And we also have billions of people generating data on their everyday life. So it means everything on the planet can generate data, either passively or actively. And there is no limitation at all, right? And second, the amount of data we can generate and collect has no boundaries, especially when comparing to the former factors like land, labor, and capital. They all have certain limitations. For example, the land supply on Earth is fixed, right? It's really easy to understand. Once a building is built, it cannot be used to grow crops. And the third reason, data never diminish during the production procedures. They can be reused over and over again, while still remains their original quality and quantity. Last and most importantly, all the other four factors can be digitalized and analyzed. However, we are still facing many challenges when dealing with data. For example, in urban computing applications, the data are isolated in different organizations, and the utilization of data are far from thorough, and there is no mature ecosystem for data acquisition, management, and analysis, and so on. So this is a background. And the above opportunity and the challenge is more obvious in the urban computing area. Then as we know that the rapid progress of our urbanization has modernized many people's lives. And in the meantime, it also generated a lot of issues, such as listed in the figure, the traffic congestion, the air pollution, and energy consumption, and so on. Then tackling this challenge seems nearly impossible many years ago, given the complexity of the city. But now the advantage of our sensing technology and the large-scale computing infrastructure have generated a vast amount of diverse data and provided us with the platform. When used correctly and combined with our AI technology, the data can help us tackle the challenges we're facing in cities. So motivated by this opportunity, we came up with the research field of urban computing in 2008, founded by Dr. Yu Zheng. It's comprised of 4 layers, including the urban sensing layer, the urban data management, and the urban data analysis, and the service providing. So these 4 layers form a loop, which enables us to solve urban challenges iteratively and continuously. So in the following sections, I will go through each layer and discussing its challenge, the research topics, and the representative techniques. Right, the first layer we are going to discuss is urban sensing. I will first introduce the challenges, then I will introduce the paradigms of urban sensing based on our experience of real-world applications. Okay, and in this sensing layer, we collect a diverse of data through IoT sensors or using people as sensors. And there are 4 categories of challenges in this layer. And they are resource allocation, the first one. And for example, we want to select the best locations for new surveillance cameras. And the second one is biased sample. For example, the traffic flow of taxi cabs is only a small portion of the whole traffic. And the third one, the data sparsity, which means we only have very limited sensors comparing to the unlimited space we want to sense. And the last one is data mining because of the communication failure or device errors. And in the next sections, I will discuss all these 4 challenges separately. Okay, the first challenge is the optimized resource allocation. Where we have limited resource, of course, right, to deploy sensors in cities, we're trying to collect data as more as possible and as useful as possible. Then how to deploy sensors remains a challenge. For instance, in the left figure of this page, we have a budget to deploy the charging stations for electric vehicles. Then which 2 road segments should we deploy the charging stations so that we have the maximum number of vehicles passing by? And notice that the tools is our virtual budget here, right? We don't have unlimited resources. Then this is in fact a maximum K coverage problem over the trajectory data, and it is NP hard. And in some other cases, we don't even know how to evaluate a deployment. For instance, in the right figure, we hope to build 4 environmental monitoring stations, like the red points on this page, in order to better monitor the air quality of the entire city. However, it's hard to define the term better here, right? Because we don't know the air quality of the whole city in advance. We only have very limited numbers of monitoring stations, like the blue points on the map, and they only cover very limited space. And for the rest of the areas, we don't know their readings. Then how to define an optimal deployment for these another 4 new stations remains a challenge. So the definition or the measurement is not clearly defined in this problem. Okay, then the second challenge of urban sensing is biased samples. So what we can obtain in a city is usually a sample of the entire data set. The distribution of some properties in the samples may be very different from that of the entire data set, which is very normal to in our research. For instance, in the figure, we can collect the GPS trajectories of taxi cabs, which is only a portion of the traffic flow in the entire city. Then how to derive the entire traffic flow based on the taxi flow remains a challenge, because the distribution of taxi cabs may be very different from the private cars on some roads. In other words, we may observe many taxi cabs on some road segments, but very few private cars. And on the contrary, there may be many private cars, but very few taxi cabs on another road segment. So this means we cannot simply derive the entire traffic flow by multiply a factor to the number of taxi cabs we observed, because the distributions are nonlinear and quite skewed, such that how to deal with this problem, it remains a challenge. Okay, and the third one, data sparsity. The sensors we deploy in a city is very limited and sparse comparing to the scale of the city, like we mentioned before. Then how can we derive the fine-grained information from this sparse sensor data remains a challenge. For example, there are only several dozen air quality monitoring stations which are sensing the air quality of a whole city. Then how to infer the air quality of each 1 by 1 kilogram grid remains a challenge. And it's also, it was a research work we have done before. Then the last challenge of data sensing is the missing data. Actually, the data missing is different from data sparsity. It means that we lost data that is supposed to be received, even if we have a sensor deployed. This can happen due to the communication errors or sensor mix functions and so on. So, for example, in the left figure here, each green point means readings we have successfully received. And the white point means that data we lost. It's very hard to fill in the missing values in spatial temporal sensor data because we don't really know when and where the missing value occurs. And it's almost random, and the sensor readings change over time and location non-linearly, which means you cannot simply fill this missing value by some linear interpolation algorithms and so on. And there is an example in the right figure. We have S1 here and S2 in the center. It has a closer distance in the geographic space. But S2 and S3 here, they're both deployed in shopping areas, such that S2 and S3 have a similar surrounding environment and share very similar air qualities, even if the distance between S2 and S3 are actually further than S2 and S1. And this can be easily depicted from the rightmost figure, where the readings of S2 and S3 are quite similar. They follow the similar patterns. And S1, which is the green one, are quite different from these two. So this means that we cannot measure the similarity between sensors only based on their geographic distance. Then how can we collectively fill the missing values based on the temporal and the spatial neighborhoods? It remains a challenge. Okay. All right. Then in the previous section, we discussed the challenges of urban sensing. Now we introduce some sensing paradigms that we follow in real-world applications. In the real-world applications that we have done in recent years, the sensing methods can be divided into 4 major categories. And the first one is a sensor-centric sensing here. We have the fixed sensing methods, such as air quality monitoring stations, the water quality monitoring stations, surveillance cameras, weather condition monitoring sensors, and etc. They are usually deployed in a fixed location and continuously generating sensing data. And in addition, we also have mobile sensing methods. For example, here, we can deploy air quality or noise detection sensors onto some vehicles, and they can sense the surrounding environment when they traverse the whole city. And we can also acquire the GPS data from cars or cell phones with GPS module. And many cities has deployed the bike sharing systems, and we can also collect the bikes locations with the, either GPS or other localization devices integrated. Okay, this is the first category of sensing method. And the second one is human-centric sensing. We can also call it the urban crowd sensing. This kind of data is not usually used well in urban applications, especially in traditional city management applications. Actually, it includes the 2 parts. The first one is a passive crowd sensing. The second one is the active crowd sensing. And as for the passive crowd sensing, such as the traffic card swaps, where the system records data whenever we catch a bus or a subway. And we also have mobile traces, which are generated whenever our cell phones make contact with the mobile signal tower. And it can generate course trajectories of people, as well as the real-time density of crowds within an area. And this data is usually used in our applications. And also, we have active crowd sensing methods. For example, hotlines are called whenever a city resident reports a complaint or emergent events, and we collect them together to reflect the whole city's the current status. And also we have those check-in data, such as the Yelp check-ins, or in these days, the COVID-19 status check-ins. These check-in data can reflect people's locations, their trajectories, and also their preferences. Okay, to better manage the city in an intelligent and accurate way, if we can sense the pulse of the whole city as complete as possible. This is why I spend so much time on this part. And in other words, the more data we collect in the city, the better we can manage it, and the later analysis and later develop the applications. So the following slides show the real system deployed in a city, which collectively senses the 4 categories of data we mentioned before. First, in this slide, we access large number of fixed sensors, including 1 million IoT components and 100,000 surveillance cameras. And these devices help us sense the city 24 hours a day. They never rest. Okay. And as for the mobile sensors, we access the 4,000 mobile vehicles, including the taxi cabs, buses, trucks, and the boats. In addition, we also deployed a dozen drones, which can be used for specific monitoring tasks. And as for the active crowd sensing, so these data are collected from people, and we collect the daily events reported from 7,000 government officers, and also hundreds of thousands of complaints of local residents. And these data are very important, as I mentioned before. They provide the complementary observations comparing to the previous sensor data. There are like actually 2 kinds of different data. And the last one, as for the passive crowd sensing, we access to phone trace, the social media data of millions of local residents. And after masking the privacy information, this is also very important. And these data also provide general observations of the whole city, such as whether it is crowded in a certain area and the events of people's concerns. Okay, so in the second part, we will discuss the challenges and solutions with regard to the urban data management. So through the urban sensing, we have collected a diversity of data, and the majority of which are associated with the spatial temporal properties. We call them spatial temporal data. In this workshop and in spatial, I think these words are very commonly used. And it seems there are many different types of data in different applications. However, according to our data structure and the spatial temporal dynamics, there are only 6 types of data, and we summarize them into 6 types of models. Why this is important? Because of the model and the type, we can define data management and the machine learning algorithms for each type of data. We don't have to develop them for thousands of different types of data, just 6 of them. And this is very important. It makes our system scalable and reusable. Okay, then firstly, according to the data structure, there are 2 categories of data as shown in the 2 rows. This is the first row, is the second row, and they are point-based data. And another one is called the network-based data. And secondly, according to the spatial temporal dynamics, the data can be categorized into 3 columns here. And in summary, there are 2 by 3, 6 data types. Okay. All right, and let's go through them each one by one. So the first type is a point-based spatial temporal static data. A representative data set in this category is point of interest data, such as the restaurant, the shopping mall, and the bus stations. Once the restaurant has been built, their locations and properties does not change over time, right? So that it's called a spatial static and also temporal static data. And the second category in this role is the point-based and the spatial static and temporal dynamic data. The most representative example is IoT data. Once we deploy a sensor, its location is fixed, but readings generated by the sensor change over time, right? So it's called spatial static but temporal dynamic point-based data. And the last one of the first row is point-based spatial temporal dynamic data. For example, the check-in data and the Didi and Uber request data. We have different people requesting Didi and Uber in different places at a different time. And there's no connections between any two people's requests. So it's a point data, and it's also spatially dynamic and temporally dynamic. All right, and let's go to the second row. Then the second in this figure is the network-based data. The first one is road network, which is the most representative data for spatial temporal static data. It can be represented by a graph. Once the road network has been built, it does not change over a short period of time. And secondly, once we project the traffic data onto the road network, it becomes the spatial static and the temporal dynamic network data. Okay, and at last, the most complex data type in the city is the spatial and the temporal dynamic data. For example, the trajectory data, which is represented by a sequence of spatial points generated by one moving object. Okay. Then spatial temporal data is quite unique because of its spatial and the temporal properties, of course. And more specifically, let's talk about the spatial properties first. It can includes 2 parts. The first one is the spatial distance, and the second is the spatial hierarchy. According to the first law of the geography, everything is related, but near things are more related. So this is very easy to understand, and the locations with a shorter distance are more likely to have similar temperature than distant locations, right? Okay, sorry. Hold on a second. Something happened to my. Okay. You guys can see the screen, right?
No, there is no screen. No slides.
I'll share it again. Okay, sorry.
It has screen, but no slides.
Okay. Something happened to my Zoom. Give me a minute. Okay. Stop the sharing. Can you see the slide now?
Yes. That's right.
Okay, sorry guys. Okay, let's continue. Then we're talking about the spatial distance, right? According to the first law of the geography, the near things are more similar than further things. And then we also have a triangle inequality to help us pruning the search space in many applications so that we can leverage these properties when applying machine learning algorithms. And the second property of spatial is a hierarchy. It denotes different geographic granularities. For instance, a city is comprised of a few districts, and the district is further comprised of a few neighborhoods. Then the location represented by different granularity carry different semantic meanings, like this in the figure, different layers of the spatial layers. And the people are sharing actually locations within fine granularity should be more similar than those people sharing a coarse web, right? For example, people who are working together in a room, they are more likely to be related than the tourists who happens to be in the same area, right? Okay, and the other unique property is related to the temporal. It consists of 3 parts, and they are temporal closeness, the period, and the trend. The first, the temporal closeness is very easy to understand. For example, the temperature of 2 consecutive time intervals, they might be very similar. But the second property, the period, will break the first principle, and very interesting. And it's unique for the temporal data. For example, the traffic flow of today's rush hour is more similar to that of yesterday, right? Which is 24 hours earlier. But the traffic flow right now or today's rush hour is not that similar to those unrush hours, let's say 12 o'clock at noon, right? In other words, the traffic flow are similar to those with further time intervals than those with less time intervals, which is contradictory to the first property, but it is also a very interesting property we need to capture. And the last one is the trend. It's also an important property of spatial temporal data. For example, as the season goes by, people are getting up later and later, and the morning rush hour comes later and later. So we can see a clear delay of trend in the morning rush hours. So how can we consider and capture the spatial temporal property in machine learning model is quite important. Then regarding the data management, as a problem we deal with is usually a city scale and highly dynamic, it calls for a powerful computing infrastructure. And then the natural choice here is using cloud computing to handle the data. But unfortunately, the existing cloud computing platforms cannot handle the spatial temporal data very well for the following 3 reasons. The first one is that the data structure of spatial temporal data is quite unique. For example, the trajectory data is represented by a sequence of spatial points as the taxi traversing a city. Then the GPS trajectories of the taxi cabs streams into a system continuously. But we don't know how large is the data or when the trip is going to terminate. So how to manage such kind of data set is quite unique and challenging. And the second, the query is different. In the search engine, we usually retrieve the documents by issuing some keywords, but in spatial temporal data, we usually add some spatial and temporal range query. For example, searching for a taxi around the location over the last few minutes, it's a query over a spatial range and also a time window. And how to answer this type of queries efficiently remains a challenge. And third one, in the urban computing, we usually need to harness the diversity of the data. We need to compute the correlations between data sets across different domains. And this requires building a spatial temporal index in advance and such technology are missing in the current cloud computing platforms. Okay, then let's take the suspected infection crowd detection task as an example to further illustrate the challenges. As we all know that the COVID-19 has caused great trouble to the whole world and is still aggressively plaguing the whole human being. We have helped many cities in China to locate the close contacts of the infected patients with the trajectory data. As we all know that the COVID-19 has a long incubation period, which usually lasts from 14 to 21 days. And the infected people cannot remember all the others they have contacted during this period. Unfortunately, the trajectory data records the activity of people and can reflect the transmission path of the patient more clearly. So our task here is to find the overlap of patient trajectories, which is the red points here, and also the candidate trajectories within certain spatial and temporal range. Actually, this task is extremely challenging, especially when considers the accuracy and efficiency, because the virus infects people very quickly, right? And even if we can locate the suspected infections only 1 minute or 10 minutes earlier, we might be able to save hundreds of lives who might get further contacts. All right. Then there are actually two major challenges in this problem. And the one is the large amount of the trajectory data. And the other is that we need to query massive trajectory data from multiple sources here. And without an efficient spatial-temporal indexing system, this task cannot be done within a strict time limit. Okay. What's the time here? Okay, oh, I think I should speed up. And in the next section, I will discuss about the data and analytics. In this, there are several methods in the urban data analytics, especially the deep learning methods for spatial temporal data. There are two major challenges posed to urban data analytics. The first one is how to adapt machine learning algorithms that were originally designed for images, videos, and text data. As we all know that many mature machine learning algorithms now have been applied to these kind of unstructured data, especially many deep learning based models. But very few of them have been applied to the spatial temporal data because the unique properties of the spatial temporal data. Then how can we capture the temporal closeness, the period, the trend, and how to capture the spatial distance and the spatial hierarchy in our machine learning algorithm remains a challenge to us. And second, in some research fields, we usually mine knowledge from a single data set. Right? However, in urban computing, we need to harness the diversity of data. Then how to fuse the knowledge from multiple data sets across different domains remains a challenge. Now, first, let's talk about the grid-based applications for the flow prediction task. I noticed that there's a paper also use this kind of methodologies. This is established several years ago, and in this example, we partition the whole city into uniform grids, and we predict the inflow and outflow of people in each grid of the whole city. Then this is an important task for the public safety. If we know that there will be many people gathering within a certain range, and very few people will leave the region, then we are most likely to have some emergency issues. Right? And this problem is very difficult to handle because there are many complex factors affecting the flow of people. For example, the flow of people in the region depends on the flow of people in the past few hours. I remember it's called the temporal closeness, very easy to understand. And secondly, the flow of people around the region also affects the flow here, which is called the spatial distance property. And right. And the third one, even the flow of people from a region that is far away from the location we're going to predict. Why is that? This is very interesting, right? Because when some major events happen in one location, such as a celebration event in Shanghai, in Beijing, or New York, right? There will be many people taking subway, reaching the destination without bypassing the neighborhoods. So if we only consider the flow of people in your location and around your neighborhoods, you cannot actually predict the flow of people in target region. So in other words, we have to consider the flow of people in each and every grade of the city. However, the locations are mutually dependent so that we cannot separately predict one location at a time. So this makes the task really hard. And fortunately, we have the deep learning tools which are able to solve it, but how to capture the spatial and the temporal correlation in this model remains a challenge. And we'll discuss it next slide. So in order to solve this problem, we partition the city into uniform grids first, and then we project the trajectory of people flow onto the grids. And then we count the inflow and outflow of people in each grid, then formulate a matrix where each entry corresponds to the inflow and outflow of the grids. Then what we have here is the sequence of frames like this. And in addition, we also have context information such as weather conditions, the events on different time intervals. Then the prediction task changes to what does the next frame looks like in the future time, right? One straightforward way of solving this problem is to use some CNN or STM framework and apply it to this problem, but it does not work out because they didn't capture the spatial and temporal correlations. So here's what we do. We first extract the frames received in recent time intervals and put them into a component that models the closeness of the temporal property. And then we extract the frame of the same time frame yesterday and the day before yesterday. It's like a period thing. And it formed another component to model the periodical property. Right? And third, we also extract the same time frame of last week, the week before last week, and also even the last month into another component to model the trend property. Then we combine the prediction results of the three components dynamically. And later we apply the external factors like events and the weather conditions and combine the results of the two components together to predict the final results. Okay. And here we only considered a couple of frames, not all of them, right, in the model. Why? Because think about this. If we only consider recent time intervals, then there's no periodic patterns and there's no trending information. We cannot predict the flow of people accurately, of course. On the other extreme case, if we serve all the data into the model, it will be very difficult to train. But here we only consider a few frames which captures the temporal properties of the data and makes our model simpler, more efficient, and even more accurate. And all the above framework captures the domain knowledge. Then how can we capture the spatial properties? And here we use the deep convolutional neural networks to capture the spatial correlations. As we know that if we do the convolution operation one time, we capture the correlation between location within a very short distance. But if we continue to apply the convolution operation, we eventually capture the spatial correlation on a longer distance, right? However, with the deeper layers of a convolution network, it's really hard to train and its performance decreases. Then we incorporate the residual network to handle these issues. And finally, we combine the dynamics of three components with a weight matrix here. So this is the whole logic of formulating this problem. And also it represents the ideas of solving the urban computing problems with those spatial properties, temporal properties, and also how to use the existing methods. Okay, I will skip several of the slides here, and actually they tell the same stories. Okay, because of the time limits. Okay, and then the last part is about the service providing. We'll discuss first the paradigms of integrating the AI knowledge, AI algorithms with domain experts. So here we're trying to answer one question, that is how can we incorporate human intelligence into the machine learning algorithms? And here's one example, which we are going to select the locations of charging stations for electrical vehicles. For instance, in this given area, we want to deploy new charging stations. And the first step is that we have trajectories generated by the taxi cabs over past year in the city. And we can use the maximum K-coverage algorithm to select the top 5 road intersections. And in other words, these 5 intersections collectively cover a maximum number of unique taxi cabs. Okay. However, we know that choosing a new location of a charging station, there are multiple factors to consider. Besides the trajectory coverage, for example, what if there's no space? What if there's no shopping mall or restaurant that allows people to kill some time? And whether the power supply can support the new station. These are the complex factors may not be able to incorporate it in our algorithm. Then we involve human experts here that we provide the experts with the results we got the first, and they will refine the results generated by their algorithms according to their own domain knowledge, where many factors are processed in their brain. And they can refine the results by removing some locations or plugging in some new locations. Then we feed the results back to the algorithm by doing such kind of iterations several rounds. And finally, we'll get a converged result with human intelligence and artificial intelligence integrated. And we do need an approach to learn the knowledge from both of them. So this is called interactive or virtual data analytics. Then finally, in order to provide the services, we need a platform. However, as I mentioned above, the cloud computing platforms cannot support such spatial temporal data very well. And we need to build a city operation system. It can be an ecosystem that allows many other people or corporations to develop their own applications on top of the platform. And we call this platform CityOS. It has been deployed in many Chinese cities, and it can also be deployed above any type of clouds. And it has 6 types of data model integrated. It has the spatial temporal AI platform integrated, also have a federated digital gateway to bypass the data privacy and the data concerns. And also on the top is the visualization layer that we can make the things more vivid and make it easier for the city managers to handle the city. And we will discuss this in this example. So here is a real system we have deployed in Xiong'an, China. It is the foundation of digitalized city management. As we can see that we can manage the whole city with real-time sensing data and check out the status of every system. And in addition, based on the current pre-warning algorithms, which is integrated in our AI platform, abnormal signals can be generated in our platform. And beyond that, we can check the nearest people who are responsible to react to this event in real time and assign the tasks to him. So this helps people manage the city more intelligently and more accurately. Actually, they can simply manage the city like playing a game. This is our ultimate goal. Then let me summarize today's talk. I introduced the framework of urban computing, which is composed of 4 layers: urban sensing, urban data management, analytics, and the service providing. And we discussed the research challenge topics and the representative techniques on each layer. Then we emphasize that the spatial temporal data is quite unique and it's very hard to deal with. We need to spend more effort to work on that problem, and we need a platform. It's called Urban Computing Platform, or CityOS. And this city operating system allows many people to work on urban computing tasks, applications, and allow those building their own services efficiently. And also, there are many challenges beyond technology to be handled. And I think if we have time, we can discuss this later in another talk. And this is also a long story. Okay, that's all for my presentation today. I'm sorry for the data for the time limit. And we have several books. Maybe many of you have also read them. But if you haven't, there are a lot of like series and the frameworks in urban computing and computing with spatial trajectories edited by Yu Zheng and our group. Okay, thank you guys.
Thanks Trish Mo for his great keynotes. So any question from the audience?
Sorry, I have a question. Thanks for a great talk. I'm very interested in the air quality prediction. You know that in reality, air quality station is sparse in space. So how to make such fine-grained prediction, such as 1 kilometers times 1 kilometers?
I think I missed one sentence of your question. What did you say about the challenge of the grading?
Okay, air quality station is sparse in geographic, but how to make such fine-grained prediction?
Yeah, actually, this is the main goal of our work in this paper, and the basic idea behind this is that we have air quality stations like a dozen, like 35 or something on the whole map or the whole area of Beijing, right? As you mentioned, and I think if you count, it only makes up a very small percentage of the whole coverage. And the idea behind this is that when applying the temporal property and the spatial property, and also like the POI distributions and the areas underlying context information, such as the road network and how many people are there, all these information can be propagated from the grades with the stations. For example, those 35 grades with the monitoring stations, and to estimate the correlations behind those features, and also ultimately the air quality sensing value of other places. So this is the underlying logic. And as for the details of the technique, you can refer to the paper, right?
Okay, thank you.
Okay.
Hi, Dr. Mo.
Hi, how are you?
I'm fine. Hi, Dr. Mo. I have one question for you. In the
is the signal okay? Can you guys hear him right?
Zhishen, your voice is not very clear. We have another question in the chat box. Trish, can you answer it first?
Let me
Is there a unified modeling available for the complex spatial temporal dynamics?
I think I should, okay, let me take about this. Is there unified modeling available for the complex dynamics? How do you define the uniform modeling? Actually, in our framework, we model those complex dynamics or the data properties into 6 different data types. Is this question related with this one? Can you speak out? No. Okay, I think I will discuss with him later offline. Then okay, I think I may have some questions to this question. Okay, here's Zhicheng's question. could you clarify the statement that it's sometimes hard to define the measurement in the resource allocation? Okay, I will answer this question first. Yes, in some urban computing applications, actually the measurement is not that obvious. I take an example here, the deployment of air quality monitoring stations. Actually, the task is to deploy more sensing stations such that we can better sense the air quality of the whole city, right? You see that this is a task without a clear definition, because we only have like several dozen stations we discussed before, and everywhere else has no monitoring stations. They're like a void on the map. Actually, technically, building a station arbitrarily on any other place is useful, right? Because we do acquire the air quality which cannot be obtained before. However, we all know this is wrong, especially if we put the new station like right to those existing ones. Actually, there might be many feasible definitions of measurement, and it depends on the requirement of that application. For example, in our previous work, we defined the problem as selecting K locations to deploy new stations, such that we can minimize the overall inference uncertainty of the whole city. And in that work, we have two tasks. The first one is to infer the air quality of each grade of the city. And the second task is the resource allocation. And during the first inference module, we derive an air quality estimation together with an estimation distribution entropy. And this estimation distribution entropy acts as a measurement of inference uncertainty. Then the physical meanings of this measurement is clear here, that we want to build some new stations in order to reduce the inference uncertainty of the whole city, right? So this is called the unclear measurement definition, and you will have that encounter with that problem later in other applications.